All right, so you know those wavy graphs from math class, right? Sine and cosine. They're everywhere. But have you ever really stopped and thought, where do they come from? Well, we're going to dive into that because the secret origin story, it's actually super simple, really elegant, and it all starts with a circle.
So yeah, that's the big question for today. How in the world do you turn a spinning wheel into a wave? I mean, think about it. One thing is going around and round, the other is going up and down. They seem completely different, right? But what you're about to see is that one is literally just the other, but unfolded.
Okay, to get our heads around this, let's picture it. We're at a carnival, and we're just going to watch someone on a Ferris wheel. But this is a special math Ferris wheel, so its radius is exactly 1. And our passenger? They're going to start their ride at the 3 o'clock position. That's what we call an angle of 0. From there, they're heading counterclockwise.
So the waves we're about to build here, they have a name. They're called sinusoidal functions. You might also hear them called periodic functions, and that word periodic is the key. Why? Because just like our Ferris wheel just keeps on spinning and spinning, these functions repeat their pattern over and over again in a totally predictable cycle. It's a continuous wave.
All right, first things first, let's just focus on one thing, the passenger's height. That's it. As that wheel spins, all we're going to do is track how high up or how far down they are from the middle. This up and down journey, this is the secret to unlocking our very first function, the sine wave. And here it is, the big reveal. The word sine, it's just a fancy name for the vertical position, the y-coordinate of that point on our circle. As the angle changes, the height changes. Seriously, that's it. That's the whole secret. Sine is just height. Okay, let's follow them for the first half of the ride. Right at the start, at an angle of 0, they're right in the middle, so their height is 0. Makes sense. Then they go up a quarter turn, up to pi over 2 radians, that's the very, very top, so their height is now at its max, 1. Then they start coming back down, and when they hit the halfway point at pi radians, boom, they're back in the middle. Height is 0 again. All right, now for the second half of the trip. From that middle point, they keep going down. When they hit 3 pi over 2 radians, that's the absolute bottom of the wheel, they're at their lowest point, a height of -1. And finally, they come all the way back up, completing the full circle at 2 pi, and they're right back where they started, on that midline. Height is 0. And that's one full rotation. And this is where the magic happens. If we take all those height measurements we just tracked and plot them out against the angle, it's like we're unrolling the circle's motion over time. And what do we get? That classic, smooth, up and down shape of the sine wave. We literally just turned a circle's height into a graph. So that was height. Simple enough. But wait, what about the other direction? Let's reset and go back to our Ferris wheel. This time, forget about up and down. We're going to track the passenger's horizontal position. How far left or right they are from that center pole. And yeah, you've probably already guessed it. This side-to-side measurement has a name too, cosine. The cosine is just the x-coordinate, the width, if you will, of our passenger's spot on the circle. So think of it this way. Sine tracks the vertical, cosine tracks the horizontal. It's the other piece of the puzzle. Let's do the same thing we did before, but for width. Okay, at the start, angle 0, our passenger's all the way to the right, so the width is at its max, 1. When they get to the top, at pi over 2, they're right above the senate pole, so their horizontal distance is 0. Then, over at the far left, at pi radians, their width is -1. At the bottom, 3 pi over 2, they're centered again, width is 0. And then all the way back to the start, at 2 pi, they're back on the far right, with a width of 1. And no surprise here, when we unroll this journey and plot the width against the angle, what do you know? We get another beautiful wave. This is the cosine wave. And yeah, it looks a lot like the sine wave, but look closely, it starts at a totally different point in the cycle. Okay, so now we've got 2 different waves, one from tracking height, the other from tracking width. But here's the crazy part. They both came from the exact same spinning circle. So let's put them right next to each other and see what's really going on here. So when you look at them side by side, the difference is super clear. The sine wave, that's height, right? It starts at 0, goes up, then comes back down. But the cosine wave, the width, it starts at its highest point, at 1, and right away it starts to go down. They're just tracking 2 different parts of the very same ride. And this quote really nails it. Sine and cosine. They are basically the same wave. The only difference is that one is a little out of sync with the other. We call that a phase shift. The sine wave is just the cosine wave, but kicked over by pi over 2. That's exactly 1/4 of a turn. So they're not two different things, they're just two different views of the same perfect circle.
Okay, so far, we've been using this perfect little Ferris wheel with a radius of 1, but real life isn't always that neat, is it? What if the Ferris wheel was bigger? Or maybe it's lifted way up off the ground? Or what if it's spinning faster? This is where things get really fun.
And that's the exact question we need to ask. What happens when that circle isn't centered perfectly and doesn't have a radius of 1? Well, it turns out any change you make to the circle has a direct, predictable effect on the wave graph.
It's actually a perfect match. If you change the radius of the Ferris wheel, make it bigger, the wave gets taller. That's called amplitude. If you move the whole wheel up, the whole graph shifts up. We call that a vertical shift. And if you make the wheel spin faster, the wave gets all squished together, changing its period. Every change to the ride changes the wave.
So let's circle back to that main idea, repetition. Because just like our Ferris wheel could, in theory, just spin forever and ever, these sine and cosine waves do the same thing. They just repeat their cycle endlessly, off into infinity in both directions.
And the magic number for one full cycle is 2 pi. That number, 2 pi radians, represents one complete turn of the wheel. Once you hit 2 pi, the whole pattern of heights and widths just starts over from the beginning exactly the same way. And it'll just keep doing that forever. Okay, but why should you care about any of this? Well, because our universe is absolutely full of cycles. This isn't just some abstract thing you do in math class. These waves are literally the language we use to describe sound waves, light waves, the AC electricity powering your stuff right now. So many things. It's this beautiful, amazing connection, showing how simple spinning motion is the building block for all sorts of complex patterns we see in the real world. So in the end, the wave was never really separate from the circle at all. It was just hiding inside, waiting to be unrolled. Now that you see how they're connected, maybe the next time you see something that repeats, like the swing of a pendulum, the changing seasons, even the rhythm in a piece of music, you'll see a little hint of that perfect circle just spinning away under the surface.